Yeah. Satyan sir, shall I start?
Yes, sir. We can start.
Yeah.
Yes, sir. Please go ahead. Thank you.
Yeah. I'm just checking the speaker, sir. Can I just say something? Hello, Satyan sir.
Yes, sir. Am I audible?
Wait 1 minute, sir. 1 minute. Try now.
Am I
Okay.
audible now?
Yeah, you are audible. Wait 1 minute. 1 minute.
You're also audible. You're...
Yeah.
I can hear you clearly.
Oh, great. I can hear you clearly. Okay, then we can start, sir. Fine.
Yes.
Yeah. Okay, everyone. There are 285 plus participants are there as of now. I hope they will start, remaining people start joining. Okay, so yeah, let's revise. A very good afternoon once again. Let's revise what have we done yesterday, right? I hope you have gone through the video if you need it, right? So in yesterday's session, we talked about the quantum parallelism, okay, right? So any function, any computation task you take, whether it's a classical computing or a quantum computing, it's all about finding a functional values for a given argument values, okay, right? That is a one very important thing. So classical computing wise, depending on the argument length, the data size input, you might go on to choose a parallel computing. If each computation task doesn't imply or doesn't like influence the next task, means there is a disjointness is there between the each computation or each argument processing. In that case, parallel computing is possible, and then you would implement parallel computing to reduce the computation time. Okay, so similarly, if such thing is possible in quantum computing, again we look for a functional processing. Okay, so one interesting thing about quantum computing here is the input arguments are converted into the binary basis. All right, for example, in our case, the input argument x value 0 to, let's say, any number would be converted into the basis of quantum qubits. If it is a one-dimensional quantum system, sorry, 1 qubit or 2 qubit, 3 qubit, and n qubit. Depending on the data size, how many number of qubits are required, you can go to figure it out. Okay, right? So this is what my note says here. If you can see, the input argument value x goes in. What is the functional value of f of x? Okay, functional value of the f of x, we are going to find in terms of the target, which is going to take the essence of x and convert that into f of x, which is going to edit the target y. So the y ancilla, we deliberately take it as 0. In that case, we will get the functional values of given argument transferred onto the target. Okay, so when I do it, I will get feeding all the argument value in one shot to the quantum function. Okay, and you would get the result or the functional values in the form of quantum superposition states of all the inputs. Okay, how it is done, we have seen for a 2 qubit case, 3 qubit case we have seen yesterday, a n qubit case we have seen yesterday, right? So depending on the size, you can always adopt your quantum gate or a unitary functional gate and find it. Okay, so one important thing Okay, before getting into the Dutch algorithm as part of our discussion today, one very important thing here in quantum parallelism, is if you take a function which takes the input 0, 1 tensor to the power of n as an input, it takes this as an input and gives out 0 or 1 as an output. Okay, so that is a function. The question is, it's not a function as it is a unitary matrix, or I should not say unitary of x, I should say u of f of x. Okay, right, where x is having 0, 0, 0 up to n times. Okay, it just goes on 1, 1 up to n times. Okay, so this is the argument x would look like when it goes in. Okay, so if I have to write in a ket notation, you just going to put a ket notation accordingly. Okay, and whatever output 0 and 1 you are getting, right, output 0 stands for yes, output 1 stands for no. Whatever is task you are doing, the task, let's say for a given argument value, whether I'm searching for a number, let's say among 0 to 2 to the power of n, that much size dimensional system input. Among that, if I'm searching for a number, let's say 0 to 9, I'm searching for 7, I would see whether the function is giving me the result 7 or not. If my code runs goes to no, means I have to search for another argument value. Okay, right? So okay, f of x is equal to 7, that is I am searching among 0 to n data points. Okay, right? So that is a quantum parallelism for you. I hope you understood completely, and if not, you please again go back and try to understand. Okay, so in today's session we will start. I hope there are no questions there. Okay, yeah, absolutely, people are saying just good afternoon. Okay, so there are no questions, so we'll go on to discuss for like based on that quantum parallelism we can go further. That is a Dutch algorithm. Okay, so we said in the very initial days, like a first class, I guess I was saying Richard Feynman introduced or gave a spark for quantum computing. Okay, and David Deutsch took the idea and started working on building a mathematical model which does some computation. Okay, so that is what we were going to discuss today. And before going there, let me give one information here. Quantum Dutch algorithm is in fact combines, this Dutch algorithm actually combines two things. One is the quantum property, that is the thing which happens at the quantum regime, an action or an event occurs at quantum regime. Okay, what is that? Is quantum interference. Okay, it is called interference. The other task it is going to combine is the quantum parallelism. We just know what is quantum parallelism now. Now we want to know what is a quantum interference. Okay, I hope you all know and studied. I think interference means some things interfering. Okay, So the best thing to recollect what is the interference, let's say we usually say, I don't want somebody else interfering in my work, so that I should, like, I can concentrate and finish my work in time. Let's say if somebody interfere, you may, like, if somebody is interfering, if they don't know anything about the task you are doing, they are not in sync with your way of working, they're going completely out of sync, and in fact they are creating a hurdle for you. In because of that, your task may not be finished and you end up in not finishing the task. So that is why usually you say you don't want somebody else indulging or interfering in your work. Okay, provided if they are very good, let's say they know exactly what you are doing, let's say you're executing a task, okay, they have full-fledged idea what you are executing, and then they come along and they give a helping hand. In that way you would feel, okay, this guy knows everything what I'm doing, he is like a helping hand to me, I would happily allow him to work along with me. Because of the extra hand coming into the same task, you would finish the job much quickly, because it is constructively interfering, two people are constructively interfering, that is leading to a positive result. Okay, when they are destructively interfering, you see the real world scenario, like, things are negative effect. As we know, constructive interference, for sure, it doesn't matter if it's a quantum or classical, quantum constructive interference leads to a positive result, and destructive interference, okay, leads to a negative result. Okay, so negative result, that is for sure. Now it is a real world applicable either at classical or even at a quantum regime or quantum level. Okay, so in real world scenario, I don't want to name any other example, but I just give a simple example. We know that now let's get back to at a quantum level. At a quantum level, okay, so at quantum level, the simplest example is very simple example. Everybody knows it. What is that? Is Young's double slit experiment. Young's double. At least people might have heard about it. It is a part of 11th and 12th and even 9th standard physics, I guess. Okay, Young's double slit experiment. Okay, right? So what it says is, if I have a coherent light source, coherent light source means a laser light kind of a thing. Okay, laser. Okay, a light source is there. Okay, so I just for our comfortability, laser means it's very like very much concentrated, very thin. Okay, for our comfortability to understand, okay, let's say the light source is there. Okay, a light source which is coherent, by the way. Let's say it is, light is coming like this. It is not, it's very streamlined. So I'm just talking in terms of within that streamline. Let's say I have a screen. Okay, so this is a kind of a hole on the screen, hole on the screen. Now light rays comes in and hits this. Okay, in fact, this is a light source at the left side. This hole itself acts like its own source. Okay, I would call this as a light source 1. This is the light source 2. Okay. Remember, this is a coherent light source. What I mean by coherent means, coherent light source, if I just take, if any ray, if you take any ray which is going, if I just take another ray which is also going along with it, okay, at any point, spatially or temporally, let's say take spatially, let's say this wave and this wave peaks at the same time. Okay, this is also peaks at the same time, and also they just goes down at the same time, peaks at the same time, goes down at the same time. Okay, so there is a nice phase. Both is the other one, the ray 1, ray 2, both the rays are increasing their strength in a same direction, same phase. It's like dancers dancing on a stage. Okay, that is just a temporal. In a time, if I see, they are increasing. In a space, if you see, they're actually moving in a sync. Let's say the extreme and two people are in sync. In time, also they are in sync. So that is what the coherence, the simplest example for a coherence for you, coherent light source. So there should exist same, there should be in phase, the frequency should be same between the rays. Okay, and I can also convert, if at all, if there is any difference in them in phase, that difference in phase would remain same throughout. Okay, so what is that idea is, let's say one is peaking like this, another one is peaking little bit later than that. Okay, you see, this wave is peaking at this point, this wave is peaking at this point. The time difference of when they peak would remain the same throughout as wave propagates. So that either they are in fixed in phase or they exist with a phase difference of, let's say, some time. When they peak, I can represent the time either in terms of some radians, let's say some pi by 3. That phase difference of angle increase, a change in the increase when they increase remains same throughout the wave propagates, throughout the ray, light source ray you take, that is fixed. Okay, so this is in phase. Okay, let me say in phase, and this is, there exists a phase difference, okay, which is going to remain same even after traveling traveling for very long distances. Okay, that is what I mean. It's like two dancers, sorry, not two dancers, 10 dancers dancing on a stage. Even though there is slight variation between them in their movements, maybe one guy is short, another guy is tall, but they appear to be in sync. But because of that, this, like their dimension, their structure, we would see there is small difference, but it still appears to be very sync, because throughout the dance, throughout the entire dance number, they are in sync. So that is what I meant. So this is a coherent light source for you. From that coherent light source, if I just take a part of it by creating this slit, it is called double slit. Okay, a screen is there, it is opaque screen, means it is not transparent, you will have small holes. So those small holes would act like their own light source. Now you put a screen at the end. Okay, this is a screen, call it as a screen. Okay, now what happens, as we know, light would travel from the hole onto the screen. Okay, right? So this small light source point itself acts like its own, like let's say a bulb, a smaller other kind of a light source. Now let's take a situation, let's say take a point, light source travels and hits this point. Okay, right? So let's say it is hitting at this point, right? And also there is another light ray comes from the bottom, and exactly it's the same point in sync with the top one. So both the light source are hitting the same point in sync. So this is the point there is a constructive interference would take place. Okay, they're hitting the in sync constructive interference. So in that case, what happens? The light coming from the top signal, light coming from the bottom signal would add up and they create a maximum intensity at that point. Okay, let me take, right? Okay, I can't write. So the let me take a different color, maybe so it creates a maximum intensity. Okay, so this is a maximum intensity. Now let's take another point. Okay, another point. Let's take at this point. So light ray goes, and it is trying to hit from the. Sorry, let me remove carefully. Okay, just a minute. The screen. Okay, what I want to have like this. Yeah, it is trying to hit from. It is peaking at that point. Okay, and light from the bottom source again coming there. Okay, and unfortunately it is coming from the bottom. Okay, it is coming from the bottom. The other one is coming from the top, the bottom one going from the okay, how do I remove this? Yes, the other one coming from what? Okay, right? So one is going from the first one comes from the top, second one comes from the bottom. They're completely in opposite phase. One is trying to pull up, another one is pulling to pull down. Let's say if a stair is there, two people are trying to sit on that and they're trying to pull each other towards them. So it's like if they're of equal strength, the chair, nobody is going to sit because the chair is stuck at the middle point. That is what happening at this point. So at this point, what happens? You would not have intensity at all. So you would say there is a destructive interference. So the strength is absolutely zero. The light intensity is zero. And the next point you see there is a intensity would be maximum. Okay, and at this point intensity would be low, right? Okay, right? So if you can cross check everywhere, every point on the screen, the light would behave like this. Okay, what I mean is there is a constructive interference, there is a destructive interference. So this is a constructive interference, and wherever there is no strength, which is actually a destructive interference. This is a point called destructive interference. Okay. Now people usually say the light rays comes and interfere, and they create no light. It's strange to accept for us, right? How come I am just taking a two light, so like torch lights, and just putting at same point, so it should create a large of more intensity, na? That is what the idea, right? In our cricket stadium or a tennis stadium in the night, there's so many lights are there, right? So much of lights are there. In each floodlight, if you see, there are so many individual lights. They're all coming and hitting at a point, and they're creating a maximum intensity. Why there is no destructive interference there? I would like I see everything is constructively interfere. Okay, so remember the light source being used there is a conventional light. It is not a coherent light source. So the light rays within that the rays coming from that light source, they're all having no coherence between them. Okay, so we would not see a constructive or destructive interference. Probably we'll see all of them coming in, creating a positive effect, maybe intensity increase. That is what you see. But when I take a coherent light source like a laser light source, or even there is something called sodium vapor lamp, okay, it is like a lamp consisting of sodium atoms inside. We excite the sodium atoms inside, and they excite and they come back to the ground state by emit the light. Sodium vapor lamp may be yellowish color. It's like regular olden days lamps. So interestingly, all the atoms inside that lamp would excite at a time, de-excite at a time, and they emit the light rays, and all the light rays interestingly would have a coherence, whatever I was showing. Okay, so the example of coherent light source is a laser. Another one is sodium vapor lamp. So there is a vapor, sodium vapor inside a lamp, which is just like a normal lamp where there is a filament. Okay, so inside there is a sodium atoms. Okay, so that is also a very good coherent light source. So there are other light source, but these are the two examples, is fine. Now if you just take this Young's double slit experiment, the light rays are coming and interfering constructively and destructively. It is a quantum process by nature, because each particular ray coming in, they say a ray is like connected to a photon. Photon is a quantum particle of the a pocket of quantum energy. So this quantum photons are coming and interfering, constructively and destructively interfering. It's a quantum process by nature. Okay, it's like 2 qubits of photons are interfering and creating, right? So it is like 2 qubits, okay, traveling, like a traveling qubits are photons, okay, traveling, interfere either constructively, okay, or destructively, and constructive interference creates a maximum intensity, okay, and destructive interference no intensity. Okay, so this process of creating a positive and negative intensity is actually called, okay, right, let me draw that. So there is a bright, there is a dark, bright and dark, bright and dark, bright and dark. So this is actually creates interference pattern where there is a bright line and dark line. Okay, right? So if I create such instead of lines, I can create something called rings, dark ring, bright ring. So there's something called Newton's rings experiment with a coherent light source. Usually people do with sodium vapor lamp. So there also we can find interference pattern. So the interference pattern, whether if you get the interference pattern from the light source, means it is a direct indication that light source is coherent, right? So it's a given. Coherent light source creates interference, okay? And if interferences, if there is an interference, then must the light source which is from where it is created is a coherent light source. It's a given. Now the photons are interfering, okay, 2 qubits are interfering. So 2 qubits can interfere constructively and destructively, okay. So Deutsch took that idea and he combined the interference with the quantum parallelism. Quantum parallelism plus quantum interference, okay, he combined it and see if we can get some good effect out of it. What is that good effect, sir? Good advantage out of it is, in fact, Dutch brought the idea is, just now yesterday we saw, for a given argument value x running, let's say 0, 1, 2, 3, 4, so on, we feed in those numbers and we get the functional values, of f0, f1, and so on up to some number fn. We are doing it using quantum parallelism. Quantum parallelism allows us to find this entire excuse me, something happened. Just give me a minute. I'll re-log in with my hand notes. Okay, I'm sorry. One minute, huh? I should have not said leave there. Every time I have to put in the okay, wait a minute. I just trying to join for the old session. One minute. I'm sorry, huh? Okay, if there is any questions, you can type. Day 9, they said already today. So I was trying to join there. Should join here. Yeah, if you have any questions, please type in the chat message. We will see. I have shared a Canvas notes yesterday. Okay. Yeah. Right. Okay, let me share the screen. Entire screen. Okay. Okay, just a minute. Cancel. Okay, screen is shared. Right. So hide. Let me use some notes. Keep. I hope my old notes is there. Okay, what is happening? Okay. Yeah, it is there. Okay. Where is my old notes? It is deleted, is it? Very bad. Make the current. Okay, there are questions. I'll see. It is there in the trash. No, it's okay. Anyway, in my recorded part, it is there, so you people can. Okay. Right. Now, okay. So where were we are at Dutch algorithm. Okay. So Dutch algorithm is okay a connection or the addition of quantum parallelism plus quantum interference. Okay, right? So quantum interference is adding constructive and destructive. Parallelism is finding functional values simultaneously. Okay, many functional values finding simultaneously. And Here there is a constructive and destructive interference. Okay, interference. And so what this guy said is, the Deutsch, he said that, can I combine them and get a very interesting behavior? What is that interesting behavior is? Interesting behavior is, if I have a functional value, let's say x1, another function value x2, can I combine and get a overall functional value? Okay, let's say some x3. Okay, so adding two functional values, I want to get the result. Not only finding the individual functional values, I also wanted to find the sum of functional values. Okay, here I am able to find individual functional values, and on the right, if I can do a sum of functional values. Okay, so that is what we wanted to do. Okay, so there is a question. I'll just wait and just check. 1 minute. Yeah. 1 minute. Yeah. So the question here is, kindly share us. Okay, in general, amplitudes of two waves may not be same. It may give rise to a partial interference. Yeah, that is also one possibility. Is it possible to make the coherent source by using normal light source? Normal light source. Okay, normal light source. Yeah, it's not possible. Given that, it's not possible. Okay, so what is the x3 here? Is it sum of x1, x2? Yeah, good question. It is not, x3 is not sum of x1 and x2. It is two functional values added. You will get some result. That functional value may be corresponding some other argument. Okay, right? So x3 need not be equal to x1 plus x2. Need not. Okay, right? Or sometimes x3 can be sum of x1 and x2. We'll understand as we go through the end. Okay, right? So how to correlate with the light particles with the qubits? Very good question. I'll clear that. Kindly, sir, share the systematic and related to this course. Systematic, I don't know. Maybe we're sharing the notes and my hand notes also. Oh, okay. Yeah. Okay, there is a question here. What is that question is? How do you correlate? Okay. So the correlation, right? So qubits for me means what? Atom, a nucleus is there. It has a valency orbit, and it can excite from the valency orbit to external another orbit which is close to that. So let's say the one which is very close to the nucleus is pulled towards it, electron, with a very large force, because distance is small. Coulombic force of attraction is inversely proportional to the distance, so less distance means more force. Okay, and this electron, if I supply a photon of energy which is exactly equal to separation between this outermost orbit to the lowermost orbit, in that case electron may jump to outermost orbit. Okay, that is not given 100% certainly, because electron may jump or may not jump. So when I just take a snapshot of this part, which is a ground state and an excited state, okay, which is, for my convenience, I use that as 0 kit and 1 kit. Now electron is in the ground. When I supply a single photon, it might go to the excited state, remain there for 1 microsecond, Okay, and then comes back and emit the same photon of energy. Okay, so nothing happened here. Excitation and de-excitation. For 1 microsecond, it is existing in the outermost orbit, sorry, or top orbit. It is like you toss a coin during the flight, you would see both head and tail. Nah? But here, in 1 microsecond, beyond that, you would see 0, 1, and then 0. Okay, so if I send a pulse of photons, okay, so there are photons, the pulse, let's say the pulse is of area pi by 2, pulse area is pi by 2. So if you go back and see in your block sphere picture, okay, let's say electron, the atom or electron which is along the x-axis, sorry, that axis, which is at the 0 ket position, you rotate that vector by pi by 2 angle. Okay, if you rotate by pi by 2 angle, either about y-axis, let's say you rotate by y-axis, about the y, this is y-axis for you, y vector, or better to use j, avoid the confusion. This is a I vector, this is k vector. Now about the y-axis, if you rotate by angle pi by 2, if you rotate by pi by 2, what happens? This vector comes along the x direction. Okay, as we've seen your block sphere representation, let's get back. What is a quantum state, by the way? Quantum state is, okay, now I should cancel it, I think, instead of leaving. Yeah. Okay. Right. I hope now pen should work. Right. So which is, okay, cos theta by 2, 0 ket, plus sin theta by 2, exponential I5, 1 ket. Now, this is what my quantum state. It was earlier, I am writing it as alpha 0 ket plus beta 1 ket, alpha replaced by like this, beta replaced by like this, with sin theta exponential, theta by 2 exponential I5. Then I have a geometrical interpretation of quantum state on a block sphere. Okay. Now, this would help me to understand what is the quantum state usually goes under transformation. When I rotate by about y-axis with the angle pi by 2, what I mean is about y-axis with pi by 2, I have to introduce those pi by 2 value here because the theta is changing about that much angle. Okay, cos theta is pi by 2, I'll have pi by 4, 0 ket, sin pi by 4. Okay, right? So the phi angle is measured from the x-axis. So it is exactly falling on the x-axis. So theta phi would be 0. Okay, I should not go to the end, I guess. If I touch there, that is happening. So psi would be equal to 1 by square root of 2 0 ket plus 1 by square root of 2 1 ket. This is what I get. So what is this effect? Rotating the 0 ket from excitation, like a ground state, to the superposition state. Okay, so this kind of an effect normally on paper, how would I write? I'll take a quantum state 0, send through Hadamard gate, it becomes a superposition state. Okay, and physically Hadamard gate action, Hadamard action is related to sending a pi by 2 pulse. Pi by 2 is the area, pi by 2 area pulse onto an atom which is where the electron is stuck to the ground. Okay, right? So if it is fluctuating, I can ensure that it's stuck to ground and then add Hadamard gate. Right? So now, if you just to send that such pulse, what happens is pulse has so many photons. the atom electron would excite, goes there, comes back. The moment it comes back, I'll have a pulse has so many photons placed in it. So then the time it comes down, it's pushed, that next photon will come and push it. So actually the electron is making oscillations, that is the kind called a Rabi oscillations. Okay, so which is equivalent to or analog to a coin being put under the flight. Means you take a coin, you create a flight. So during the flight, you see head and tail, both are there. Here also, during the superposition state, the electron being 0 and 1, 0 and 1, 0 and 1 continuously. If you try to make an observation, it falls to one of the state because it is so fragile. It's like you are going to catch a coin in the mid-flight. Okay, so if you just take an atom or an electron having the information of alpha and beta on that, it is a stationary atom, or electron is a stationary qubit. Okay, means it is stable. It's like somewhere I can put my information and it remain there. Let's say like a almirah where I put my money, it remain there. Okay, right? Now the information cannot be stationary, not process the information and do something with that. So for that, I have to send the information from one point to other point. So I can't take my atom every time and carry along. Okay, I have to put it in a very, say atoms are very fragile. You have to put it in a box, ensure that it is not interacting with the environment. Okay, so you have to put in and take somewhere else. So for that, what people thought, that realize the qubits out of, okay, dynamical system like photons are very good means to realize a qubit. Okay, how to realize a qubit out of it? Very interesting. Okay, so for me, photons means what? Photon is a part of electromagnetic wave, EM wave. Okay, so EM wave, there is electric field oscillation. Electric field is oscillating in one plane. Okay, and along the perpendicular axis, there is a magnetic field oscillating. Okay, so this is a magnetic field, and the black one is the electric field. Okay, in the red one, electromagnetic field would be oscillating, B would be oscillating. In the vertical axis, along the horizontal axis, okay, electric field would be along the vertical axis, oscillation. Okay, now this is electromagnetic for you. For electromagnetic, if you just see electromagnetic wave, usually you write electromagnetic field as E naught sine or cos kx minus omega t. Okay, you can write sine or cos, doesn't matter. Okay, right? So I am writing for sine, which has a propagation vector k, means propagation vector k. So here in this case, it is showing it is going along the x direction, and omega angular frequency 2 pi mu, the frequency of the light. Now the electric field vector is just increasing and decreasing with the oscillating frequency of 2 pi mu. Okay, it is propagating along the x direction. This is the information given. And the oscillation of the electric field vector, is it happening in the vertical plane or a horizontal plane, must be given. That is given in terms of polarization, usually given with the eta in this case. It is in the vertical plane. The propagation is along the x-axis may be the oscillation would be vertical to perpendicular to that. For time being, let's say along the z-axis or a y-axis, it is doing oscillations. So it can be anything other than x. So I'll say y. Y means j cap. Okay. So electric field vector is along the j. Okay, let's say j is vertical, propagation is horizontal, so oscillation is happening in the vertical direction. So in this case, the photon is polarized to have a vertical polarization. Okay, so photon is polarized to vertical polarization. I can put that polarization vertical to horizontal. How do I make? I can rotate the polarization vector from horizontal to vertical by using something called wave plates. Okay, so those wave plates, either quarter wave or half wave, exactly you have to pick, and you can convert using wave plates. They're like polarites. They convert vertical to horizontal. So let's say vertical is 0 vector, horizontal is 1 vector. I am doing a x operation there. Okay, so there is interesting, another waveplate is there. Okay, which takes 0, puts that into superposition, which is a plus gate state. Again, another gate is there, that is a Hadamard gate. So Hadamard gate, literally mathematical term to represent the superposition action and rotation, by the way. And when it comes to optics, it will have a transparent material, like some molecules will be there in that material. Those molecules will rotate the polarization from vertical to superposition statements angle. So you see, horizontal is this, vertical is this. Initially, the photons are along the vertical direction. Okay, along the vertical direction, right? Let me along the vertical direction. I want to move that by an angle 45 degrees. This way I want to move. How much angle I have to move? 5/4 angle I want to move, a rotation. So which can be done by Hadamard action. Okay. Now the information of the qubit, stationary qubit or atom qubit, is transported or transferred to the photon. How? Let's say the electron qubit is there, which can have ground and excited with some superposition of alpha comma beta. A photon comes along, okay, takes this information of alpha beta, converts that information of alpha beta in the form of its horizontal and vertical polarization, alpha plus beta v. Okay, this would be a photon state, and this would be an electron state, a qubit. And by interacting photon with an atom or an electron, takes that information into its polarization, it travels along. So a photon is not stationary, or it's a dynamic qubit. Okay, dynamic or traveling qubit. Okay, fine. So this is what, let me, I think, I hope this will not close down. Okay, that's a question somebody was asked. How do you correlate? Okay, there's one more question. With normal light, okay, normal light also, we can get a coherent source when the two coherent beams are generated, transmitting light source, and the two coherent beam sizes are not equivalent. We can get it. You did this experiment. Okay, young sunlight. Sunlight, please reference. Okay, let me tell you one thing. The light source of sun is one of the best coherent light source. It is actually generated out of nuclear fission. Okay, nuclear fission, the hydrogen, they combine and generate a lot of heat, and it is all the rays coming from the sun are of coherent light. So sunlight is the best coherent light source. I didn't miss that saying, but naturally occurring light source from the sun is a coherent light source. That's why you are able to see the coherence. That's why you will see when a nice thin films are created on a And a road, when it's rain, let's say some vehicle has a leakage issue with the oil. So oil is fell on the water, nice thin film is created on the water, and you would see when the sun comes back, you see nice colors. So those colors are actually interference fringes. Okay, right? What is the use of interference in between ket E and ket G? There may exist there is a ket state, so can that not be used to show some kind of a results on block sphere? Yeah, you can show the change in the quantum state on a block sphere for sure, because any change in the quantum state, oh my god, okay, I have not deleted. So any change in the quantum state, okay, it's nothing but rotation of that quantum state vector about some axis about with the some angle. Anything you take, any quantum operation you take, it's about nothing but rotating something, or rotating the combination of many rotations, you might say that, not just a single rotation. You rotate about the x-axis, then rotate about the z-axis, and rotate about the y-axis. So all the combinations, it's like a given quantum action or operation would be equivalent to product of so many rotations. Let's say u is equal to h, t, and s. Hadamard gate, T gate, and S gate. That is what we saw earlier, I think in the second class. Okay, right? So given quantum gate could be expressed in terms of many possible rotational gates. So usually a quantum computer, and if anybody design, they will not design all the gates for every operation. They will design for a fundamental operation. For a fundamental, from the fundamental gates, you can realize any other gates, like universal gates in case of classical computing, NAND gate, right? Using them, you will realize all the gates. Huh? Similarly, here there are fundamental gates like a Hadamard gate, X gate, and C0 gate. Okay, using them, you can realize all the existing like required gates. Okay, this is Kitow's theorem, Simon Kitow's theorem, which we discussed in the second class. Okay, what is the use of quantum interference? So, immediate use of quantum interference is whether light is coherent or not. We can find that's immediate, right? But in now you see Dutch algorithm which we are discussing. The one use of quantum interference is, okay, where is that? Here. One use of quantum interference is you combine with a quantum parallelism, you find the functional values, multiple functional values simultaneously. Not only that, because you added a quantum interference effect there in your calculation of interacting photons or qubits, you are also able to find the sum of the functional values or the differences of the functional values, not any sum, addition modulo sum. Okay, what I mean is you can find the addition modulo sum of functional values, or you can find the separation. For time being, you can say sum of the functional values. Okay, we'll see that. I guess we'll give a break now. We'll give a break for 5 minutes and then we'll come back. Okay. Polarizer, yeah, polarizer is the one. Okay, polarizer, what is the effect of polarizer is, if you just take a light source, it will have electromagnetic wave vector oscillating in all the directions. Okay, right? So what I mean is there is a vector oscillating in x direction, y direction, okay, and angular, and many directions electric field vector is there. Okay, it's like electric field vector actually oscillating and also existing in every direction. Now if I use a polarizer, okay, what it does, polarizer, what the effect of polarizer is, it will have something called crystallographic axis. Okay, so crystallographic axis. What happens if any oscillatory electric field oscillating thing is exactly in parallel, only that vector travels out, oscillating thing, that only electric field, everything else are cut down. So this is a linearly polarized light, linearly polarized light. This is not. This has not non-linearly polarized. So electric field vector is existing in every direction. Okay. So this is a conventional light. Conventional light. Okay. From the conventional light, you get a linear polarized light by using a polarizer. Okay. Right. So whether I want a horizontal, you take the crystallographic axis of polarizer is in horizontal direction. Or there is a way to rotate the polarizer. You can just rotate the polarizer. Its crystallographic axis rotates and you would get a linearly polarized light. Okay. Is it necessary that coherent light source has fixed okay, there's a fixed wavelength. Mostly laser provide monochromatic lights. Yeah, fixed wavelength or a fixed frequency means a single frequency. Okay, so you can create a laser with multiple frequencies, but the thing is, I see laser is how lasers are created is take a medium. They take a medium. Okay, atoms inside means medium. Okay, right? You excite each atom and excite, and they de-excite and send a photon. Okay, so you excite at a time by heating, maybe excite at a time. So all the atoms excite and they emit a photon, let's say in this direction. Okay, and this photon, if this is a mirror, curved mirror, photons reflect back and does the oscillatory action and does so many interaction with the photon atoms, and they intensify in particular direction, and let's say there is a small hole here and emit it. Okay, this is a laser effect for you. Amplification is done for every particular direction. So here only the atoms which are chosen in such a way that they excite and de-excite, and all of them excite and de-excite with the same energy differences. So excitation and de-excitation is same energy difference, and the emitted light of all the photons are same frequency. Okay, so the de-excitation should happen as per my wish. Okay, so what I usually do, they will not take a 2-level atom for lasing effect or a laser effect. They take a 3-level atom. Okay, so they put the atoms here by excitation state. Okay, so the atoms here is the number of atoms here. Let's say I'll write in the density matrix the number of atoms in state. This is 0, 1, and 2. So the atoms in a excited like a one state is much larger than atoms in the state 2. So this is called population inversion. In that case, all the atoms would de-excite and emit the light. That light is intensified and then converted, okay, intensified by putting inside a cavity, and you would get intensified laser light. Okay, this is the effect. Now all the frequencies you want to put multiple atoms, different excitation, different de-excitations, right? So that's why people only confine to one particular kind of a medium. Okay, so it's a laser principle anyway. Okay, what actually happens to physical qubit after measurement? Does it just die out because it looks like a qubit is formed from a pulse after all? That's right. When you make an observation, obviously the system would lose its quantumness. It becomes a classical. Okay, yeah, that's right. Experiment by Young produced coherent source out of incoherent source by clever arrangement. I am not getting what is the question. Yeah, I don't know. I should maybe we can have a discussion on this. What do you mean? Sorry to ask, but sorry to ask for explaining the working of a laser and reason for monochromatic light. Okay, so thank you for asking. Okay. It's required sometimes. Very basic knowledge important. How many bits are stored in single qubit? Differ from classical. Yeah, it's 2, na? Right? You guys know, right? Qubit means 0 and 1 together, alpha and beta. So alpha is the probability amplitude, beta is the probability amplitude. These are like numbers, like alpha can be 0.4, beta can be square root of 0.6. These are the two numbers. So these two numbers are 2 bits. So a qubit takes 2 bits storage capacity. If I add one more qubit, it becomes 4 bits. If I add one more, I'll become 8 bits. Okay. How? 4 bits means 2 qubits can be 0, 0, 0, 1, 1, 0, 1, 1. So it creates a 4-bit possible storage. Okay. Right. So let me store this, export as an image. Yeah, I think it is exported as an image. Even if I lose it, I have it. Okay. Okay, now I'll just take 1-2 minutes break.